Oh no, that's not fair. Okay, I was saying that the student states that temperature is related to thermal energy. What I'm saying is, let's suppose there's an object which is 1 kilogram and it's iron, and there's another object 2 kilograms that is also iron placed in the same room. So they will have the same temperature, but obviously the 2 kg one having greater mass would have greater heat energy in it as well, right? Now, so this is why temperature is not related to heat. Temperature is related to the average kinetic energy of that particular body, right? So we got to remember that. So then at change of state, you've learned this previously, a change of state, although heat is absorbed or released, depends on what kind of state is changing, but the temperature stays constant, right? So that's why you can see that obviously you're putting in heat, but temperature is not changing. So yeah, that's fine. If you have any questions here, please let me know, and so I can help you out there. Okay, kids. That's pretty good. Now let's go to this experiment. So when you're doing this experiment, you guys need to understand that we will have a heater placed uh, by punching two holes in a metal block. Suppose we have here a heater. Now heater symbol that we use is like this. So in paper 5, if they ask you the symbol, it should be like this. This is heater. And then you have placed a thermometer right next to it as well, right, by punching a hole. You basically connect it to some electrical circuit where you can measure its current by connecting ammeter and voltmeter across those terminals to find how much voltage is being supplied to the heater. The next thing you got to do is you guys need to basically cover this whole thing with insulation as well. Why do you want insulation? Because you do not want heat from the heater to escape to the surroundings as well. And we can then assume that all the heat is being transferred to the metal block rather than going into the surroundings as well. Now let's check this question, right? So in this question says a thermometer and an electrical heater are inserted into holes in an aluminum block of 960 grams. The power rating of the heater is 54. The heater is switched on and readings of temperature of the block are taken at regular time intervals. When the block reaches a constant temperature, the heater is switched off, then further temperature readings are taken. The variation with time t of the temperature theta of the block is shown, as you guys can see. So basically they're saying that it increases in temperature. At one point, it becomes constant. Now there's no increase in temperature, right? At this point. And then it is switched off, so the temperature starts to decrease. So we got to know why this is happening, right? So it says suggest why the rate of rise of temperature of the block decreases to zero. Now, obviously, you guys need to understand that we have learned that in thermal equilibrium, what happens is that when you reach a certain temperature, right? So let's suppose this is air around it, and this is 25 degrees Celsius, this 50 degrees Celsius. You've reached to a certain point. So if you are putting in some heat, it is also losing heat to the surrounding. If the heat that you put in and the heat that goes out becomes equal, then obviously the temperature is not going to rise anymore. So you guys need to remember that, right? So if I were you for 2 marks, what I would write for the first one, I would say that when heat gain by the block becomes equal to heat lost to the surroundings by the block. Then the temperature rise would stop. So this is why this is happening, that you guys need to understand that at one point, the rate of temperature, the heat loss would be the same as the rate of heat gain. So then it would not change at all. If you have any questions here, please let me know. So generally, what you want to do in this one is that when it is rising, so you guys need to understand that they have already said we took time at regular intervals, right? So regular intervals time usually in paper five. So like here, right, in paper five, we want to take this time as 5 minutes. So 5 minutes is a standard time that the examiner basically reports down there. So you got to take that as well in consideration if you're writing it in paper five. Remember that. Anyway, now, in this one, it says after the heater has been switched off, the maximum rate of fall temperature is 3.7 kelvins per minute. Okay, so per minute means that it is in 60 seconds. And says estimate the specific heat capacity of aluminum. Obviously, you guys need to understand that the input power should be equal to the minimum rate of heat loss, right? That's where it becomes same. So what you do? 54 watt is the input power, and minimum heat rate loss will be the heat supplied will be mc delta theta if you divide it by time. So basically, it gives you the power, right? Power at which the heat is supplied. So now this is 54, and we can write it as 0.960 because that was the temperature, sorry, the mass. C, we got to find this was 3.7 kelvins, and the time was basically 60 seconds. Okay. Now, C will be equal to 912 joules per kg per Kelvin. And that should be your answer. You can write 912, or according to our values, because they're too significant, so you can also come to 910. That's fine as well. Okay. Because I'm dividing it by 60, because that is the time it takes for this power to lose. That's why so long. Because you see, the formula is Q equals to mc delta theta. That is energy, right? Now, power into time is energy. You can do it like this if you want to. The power that was supplied was 54 watts, and the time that it was losing this uh, temperature was per minute. So you have 60 seconds. Mass was 960 divided by 1,000 because you want to change it to kgs. C, and the change in temperature was 3.7. So you divide it and multiply to find energy. It's the same thing. Do you get it? Salma, is it clear? Okay. So it's up to you. You want to do that. Anyhow, so going to the next, then let's check it out. So the next thing is our determination of specific heat capacity in liquids. Now, state what is meant by thermal equilibrium. We have already done that, and I'm going to do it again. So, both bodies are at same temperature. When this basically happens, so we say that these are in thermal equilibrium, but there's one condition, and there is no net. Now, this word net is the key word here. No net heat flow. It means that the heat that one body, that's what there are two bodies like this. So if one body is transferring heat of value Q, the other body should also be transferring the same amount of heat back and forth. So then you don't have any net flow of heat. So that's something you guys need to remember. Anyhow, in this particular question, it says an electric water heater contains a tube through which the water flows at constant rate. One second. Okay. So now it says that if you see water comes in, it gets heated by the soil and then water goes out, as you can see. All right. So obviously, if you measure the temperature of water that is coming in and then measure the temperature of water that is going out, this would basically give us that change in temperature. But the issue is in this particular experiment is because it's not covered by any insulation materials. So heat is also going to get lost in the surroundings. Okay, so heat loss is occurring. And if heat loss is occurring, then we need to do something about it. All right. What you should do is number one, we must repeat the experiment, but should keep the difference in T1 and T2 the same. So I'm going to explain it why you need to keep that difference same. The problem is that let's suppose if this is that tube that we're talking about, it loses when the temperature is like 50 degrees here and then you make it 80 degrees here. So the difference in temperature remains 30 degrees. So it will lose the heat according to this difference, right, to the surroundings. Let's call this loss of heat as H. All right, kids? So what you do next is basically you want to keep these temperatures same and you got to alter, you need to alter the power of heater and the mass flow rate, which means how much mass of water is flowing through this tube. So for a greater mass flow rate, you need greater power of the heater as well. So it heats it up with the same value of 30 degrees. Do you guys understand that? This is just an example. This way, you will have each time you change the mass flow rate and the power, the heat loss would stay the same as the temperature change stays the same. And we got to do that. Now, why we need this? Because if you do it two times and you subtract those equations, heat will the heat loss will be basically subtracted as well. So let me just write an equation here so you guys understand this pretty well. So what I'm saying is that you have power, sorry, you have energy supplied by heater, right? This basically goes into energy supplied to water plus loss to the surroundings. All right, so this is what's happening. Now, what you do is we're going to take energy one of the heater, and at that time, what we're going to do is we're going to use MC delta theta. Now, this delta theta is T2 minus T1. We want to keep this same. We want to change the mass of water that goes through. So it's causing a heat loss H. Then we're going to change the energy of heater, and we're going to alter the mass that flows through. And then we got to keep this temperature same. So this H, the heat loss, also stays same. When you subtract these two values, so what you're going to do is you're going to find the change in energy supplied by the heater, the change in mass times C. This will be the same temperature, and this will cause H minus H. So this will become zero. So we're basically letting heat to go out, and we keeping the conditions same so that the same heat is lost every time we repeat the experiment, and we subtract the equations to remove the heat loss from the equation so we get the exact answer. So please write this down right now, and if you have any questions, please let me know. Abu Bakr, very good. Very impressed by your time today, and Samir, you as well. Good job. Hmm. Okay, very good. So what I'm saying is, Salma, let's suppose you turn on the heater at a certain energy. Okay, let's call this energy one. You let m1 amount of mass of water flow through it. So this energy that you supply to the water will also go into the surroundings. Now this heat loss to the surrounding basically depends on how much temperature change is going to be there. Do you understand that? Then we're going to increase. Let's suppose we increase the energy supplied by the heater. So we need to increase the mass that goes through so that what we want is we want the change in temperature to be same. Why do we want the change in temperature to be same? Because we want the same heat loss. If you increase the temperature or decrease the temperature change, it would give a different heat loss. Do you understand that? We don't want that. Okay. Once you have the two equations, if you subtract these equations, so what you get, E is E2 minus E1. M is M2 minus M1. C is the same value, these are same, so it just stays same. But then what really happens is the heat loss minus the other heat loss will give us zero in the equation, which means that we have successfully removed the heat loss factor from this equation. We're increasing the mass because let's suppose you're heating 2 kilograms of water from a certain heater. Now, if you increase the energy of the heater, don't you think if we keep the mass same, it will be hotter now because you've increased the energy? Now we don't want that. We don't want it to get hotter than before. What do? We increase the mass. So if you supply more energy, the mass is also more. So basically, it heats the water to the same temperature. Do you get it? Yes, we make the heat loss constant by keeping the temperature rise constant of the water. And that we can do if we increase the mass or decrease the mass, depends on what kind of energy we're supplying, higher or lower than before. Understood? Okay. Now, in this experiment, obviously, it says that water flows into the tube at the temperature of 18 degrees Celsius, and the power of heater is 3.8 kilowatt. The water of the temperature of water outlet is 42. So this is the change temperature. It says the specific heat capacity is this. Use the data to calculate the flow rate. Flow rate means what is the mass per unit time. It is, just letting go. So what you do? Pretty simple. Energy is given as mc delta theta. You guys know that. If I divide it by T here, I have to divide T here. So what will this give me? Power equals to mc delta theta divided by T. So what you do? Power of the heater was 3.8 times 10 raised to 3. The mass we need to find. C, we have 4.2. It is joules per gram per Kelvin, right? And the change in temperature is 42 minus 18 divided by T. What do we really need? We need this mass over time actually in grams per second. So let's find it out then. What you do? Mass over time will be equal to 3.8 times 10 raised to power 3 divided by 4.2 times 42 minus 18. This should give you an answer of 38 grams per second. All right, kids? Now that's easy. This is the easy part. The real part basically starts here, where it says state and explain whether your answer in one is likely to be an overestimate or an underestimate. If you see the drawing, do you understand that we never repeated it? It means that we never took the heat loss in consideration. We have basically ignored that and we have believed that all the heat energy is being transferred to the water. In fact, some of it must have gone through the surroundings as well. So the water must have gotten less heat. So would this be an overestimate or an underestimate? What do you guys think? Exactly. So this will be an overestimate because because there would be heat loss to the surroundings as well. Okay, kids? Any questions here? Please let me know. Okay, very good. Okay, please write this down. Zainab, do you understand everything? Abu Bakr, everything is clear. Aisha, Khatija, Samir, wake up, please. Very good. All right. Samir, are you here?
Yes, sir.
Why is there a class on Friday? Saturday would be much better. Why should there be a class on Saturday? Abu Bakr, give me one good reason for that. Okay, more busy day. Juma is not at 3 p.m. Oh, sorry. For you, it is 4:30. Mhm. And what else? Actually, there's a reason for it. That is good. Actually, the interesting question is why is it Thursday, Friday, and Sunday, not Saturday? This should be your question. Because on every first Friday, I have to travel to Karachi. So usually I would end up missing classes because I'm returning on Saturdays. So that's why I cannot keep it on Saturday. So yeah, it's a majburi. Get it? So Monday I have other group. So it's Monday, Tuesday, Wednesday, another group, and then you guys stay Thursday. So Thursday, Friday, and Sunday. Unfortunately. But don't worry, Abu Bakr. From 1st April, we're gonna shift back to Monday, okay? On your request. How's that? Yeah, 1st April. Yes, it's quite near. So पता भी नहीं चलेगा you have exam. So when you will be like, uh, you will be done with your mocks. with flying good grades. So then, पता भी नहीं चला. So I gave my A levels in I think it was 2009, and I feel like that was just yesterday. So पता भी नहीं चलेगा. Just talking about months, I'm talking about years. And I've looked at. Okay, now so let's go to the next. So the next question that we see here is basically the similar sort of question. So I'm going to give this as homework because I know Abu Bakr likes the homework so much. And now we're going to go towards the specific heat capacity, specific latent heat of vaporization, right? So specific latent heat. Now, if you see this definition, it's talking about just latent heat, not fusion nor vaporization. Because it's not talking about both of these, then we need to basically write it in general terms. Now, how do we do this? Let's check it out. So we're going to say it is the amount of heat energy per unit mass, heat energy required. My goodness. Heat energy required per unit mass to completely change state the state without change in temperature. We're not going to specify now that we are changing solid to liquid or liquid to gas or vice versa. We will just write it in general terms that we are going to change the state. Anyway, if you look at the whole thing, it says that a beaker containing a liquid is placed on a balance and the heater of power 110 watt is immersed in the liquid. The heater is switched on, and when the liquid is boiling, balance reading M are taken in corresponding times. Now check this out. Here's the balance. Okay. Let's suppose we started with some kind of mass M. So every time liquid is going to get boiled, so particles are going to leave, obviously you will see a decrease in mass. So what we're doing is at regular time intervals, we are checking out the decrease in mass. So as we're checking out the decrease in mass, we can then find the latent heat of vaporization by finding that change in mass of and how much energy we've supplied in a certain amount of time. So the question then says that state the feature which suggests that the liquid is boiling at a steady rate. Now, as you can see, it's a straight line. It's a straight line. Rate is basically the change in mass per unit times. That means that it has to be the gradient of the line is constant. That is why we are saying that it is boiling at a constant rate. Is it clear, kids? Very good. Now it says use data to determine the value of specific latent heat of vaporization. Now what you going to do, like I said, specific latent heat of vaporization is given by Q equals to LV times M. This is the equation that I taught you. Now you guys should understand that Q is the heat supplied from the heater. So the heater will have some power, and if you multiply by the time for which it was, you know, given, that would give you the energy, and then the rest of things are same. Now check this out. The power they said was 110 watt. So I'm going to put it here. It's 110 watt times time equals to LV times M. Now I'm going to take T on the other side. So when I do that, it's going to give me 110 equals to LV times mass over time. This mass over time is basically the gradient. Yeah. Okay. Now, that's good. So, yeah. Anyhow, so we got to find the gradient of this line in order to find latent heat of vaporization that I say. So what you do, generally, it is a good idea to take the points which are really, really far away. In paper 5, generally what we take is we got to take at least points 50% away from each other. So take points at least 50% away. So this is, in fact, very important for paper 5. So you can write this note. Now, we're going to take one point. If I were you, I would take this point in the starting. But it's easy. That's why. So that's basically 0 and 380. I'm going to check it is in grams. This is in minutes. So, yeah. Then I'm going to check if I could take this point because this is a pretty much, on the line. So I'm going to take it here. If you see, this is about, I think, 6.2468. So that's 6.8 minutes. And this value is, if this is 330, that means 322, 324, 326. So that would be 326 grams. This is all grams. Now we're going to find change in mass over change in time. That's the gradient. So 380 minus 326 divided by 0 minus basically 6.8 times 60. Why am I doing it? Because I want the time in seconds. That's why I'm doing this. All right. If you have any questions, do let me know. Anyhow, so let's find it out. So this means if I use the calculator, it's going to be 380 minus 326, that would be 54, and then divided by 6.8 times 60. So I will get a mass per unit time as 0.132. Okay, so I'm going to use this here. 110 equals to LV times 0.132. That's grams per second. So LV will be 110 divided by 0.132. So 110 divided by answer. So that's going to be 831. You can write it like this, or you can write it as 830. It's up to you. I think so. But oh no. Wait. I just realized one thing that they have also asked us to find this in kilograms, not grams. My bad. Sorry. The answer that we get right now for LV was basically in joules per gram, the 831 one. So if I want to convert this into sort of kilograms, then I need to basically divide it by 10 raised to minus 3. That would convert into kg. So that would be 831 times 10 raised to minus 3, which basically will be 8.3, sorry, 10 raised to 3, 8.3 times 10 raised to 3, like that. Is it clear, kids? Any questions here? Please let me know. 10 raised to power 5 joule. That's a mistake here. Wait. Okay, yes. Any person who feels that this is something difficult and you did not get it, please let me know. Okay. Now, again, if you look at the whole system, the system is not insulated. They again ask you, state the reason whether the value determined is an overestimate or underestimate. What you're gonna say? Yes, yes. Is it an overestimate or an underestimated value? Overestimated. Exactly. It will be an overestimate. Why? Because because the heat lost to the surroundings was not taken in account. That's why. So that is just a standard answer that you should be writing always. Okay, pretty good. Okay, let me catch some breath now. Okay, now let's go to the next and check this out. So this is the similar question that is for you to do it now and see if you guys can manage this question on your own. Finally, if you don't, just let me know. Finally, we're going to talk about the determination of specific latent heat of fusion of ice. Now, this is a bit tricky one. I just seems easy, but it's kind of that. The first part will be your homework because it's the same definition that we've written in the last question. So do practice it here. Now, in this one, I just want to tell you something very, very important. In all these previous things, we had an equation made like this. You see, in this one, what was happening? Heat from heater would go into water plus surroundings. This is what was happening in all the previous questions that we've done. This time it will be different because the surroundings that we see, surroundings will be hotter than ice. So what will happen now? The equation is going to change a bit. How? Heat from heater plus heat from surroundings would all go into latent heat of fusion times mass of ice. Because ice will not only gain heat from surroundings but also heaters. So that is the error in this. So remember this. This is very important. Okay. Now generally, what you do is number one, we leave the ice to melt on its own due to heat from surroundings. This is the first thing we got to do. Let's call that mass that is melted as M. Then, number two, you turn on the heater and find the new mass melted in the same time, same amount of time. So let's call this M2. Now, what you do, basically, we can then basically figure out that mass melted by heater only would be equal to M2 minus M1, because the second one is basically, first one is the mass melted by the surroundings. The second one is the mass melted by heater and the surroundings. If you subtract those masses together, so then they are going to give you, that value is going to give you only the mass melted due to the heater. That's very simple. Because, Salma, because surroundings always influence that. When they're not gonna ask you about the surroundings, or they don't want you to include surroundings, then they will either ask you whether it's an overestimate or underestimate. In this type of question, they will not ask you that because they have given you two different readings to basically use so that you have to find the exact values. Get it? So there are different variants of questions. That's why I want you to solve this.
Me?
Okay? Yes.
सर अगर लाइक क्वेश्चन के ना सिर्फ ओवर एस्टिमेट वाला होगा तभी हम कंसिडर करेंगे कि हीट लॉस नहीं हो रहा और अगर मेंशन्ड
नहीं, हम कंसिडर हर एक में कर रहे हैं कि हीट लॉस नहीं हो रहा है। हम कह रहे हैं हीट लॉस हो रहा है, ये हीट गेन हो रही है, हम कंसिडर कर रहे हैं। We do not include it in the equation if they ask you it is an overestimate or underestimate, because वो हमने इंक्लूड नहीं किया तभी तो उसने पूछा ना। Do you understand?
सर लाइक हम कैसे फिगर आउट करेंगे कि लाइक हम हीट लॉस को कंसिडर करना है फ्रॉम द सराउंडिंग या ये सब?
Data, you have to consider heat loss all the time. It's not an exception. You
सर लाइक
did not consider it before in the previous questions. So after doing that part, he asked you whether your value is an overestimate or underestimate. Do you agree?
या
Now, in this one, you have to basically include heat loss as well. Why am I saying this? Because if you check this out, in the previous questions, he had only given you one value of power, one value of mass, one value of time. Do you agree?
यस
In this question, he has given you two values of power, two values of mass, and two values of rate. So that means he wants you to do something about it, right? So he will ask you to add heat loss in this. Do you
तो
understand?
सर जब दो वैल्यूज दी हुई हों सबकी तब हम लोग हीट लॉस को कंसिडर करेंगे?
In the equation, yes. Otherwise, वैसे तो we have to consider it always.
हाँ
समझ
बट
आए?
लाइक वाली वर्किंग के नाम कंसिडर नहीं कर रहे थे ना,
Yeah, yeah,
और
yeah.
इसके नाम कंसिडर करेंगे तो जब दो सेट ऑफ वैल्यूज हर चीज की दी हुई होगी तब हम कंसिडर करेंगे लॉस को।
That's right. That's right.
राइट?
Okay. Now, so first thing they have asked you is that they want you to find, they have given you the power, they have given you the mass, they want you to find the mass melted per second, which means grams per second. So the mass melted is given in 5 minutes. What you do? You have to divide 78 by 5 times 60. Why 5 divided 5 into 60? Because 5 is in minutes, you got to take it into change into seconds. What you do? 78 divided by 5 divided by 60 gives you 0.626 grams per second. Next one, 114 divided by 5 divided by 60, 0.38 grams per second. Get it, kids? Just like that. Now, they say, please understand this. They say, use the data in the completed figure 3.2 to determine the value specific latent heat of fusion of ice. Okay, let's do that. So the first of all, you're gonna make the equation. What is the equation? Heat from heater plus heat from surroundings, because it is melting. So you need to be very careful about this equation. Gives you basically the latent heat of ice, or you could say energy gained by ice. Let's be simple. Now, heat from heater obviously will be power into time. Heat from surroundings will be H, because we don't know what those were, equals to latent heat of fusion of ice times the mass of ice. Understood, kids?
Sir, P into TQ?
Because it is power beta, we need to find energy. It is energy's equation. They've given power. Energy is power into time. Okay?
Yeah.
Okay. Now write the first equation. What is the initial power? 70. Get it, kids? 70 is the power. Time is 1 second. Why 1 second? Because you have grams per second plus H equals to latent heat of fusion times 0.26, because that is the mass melted per second. Now you got to make the second equation. 110 times 1, because time is 1 second, plus H equals to latent heat of fusion times 0.38. Why 0.38? Because it's gram per second. Now you got to subtract these two equations to cancel this factor. So what you do? 110. Where do I write this? This is something important. Wait. Oh no. Let's write it here with a different color. 110 minus 70 is a right equation, 2.26, and latent heat of fusion. Is that clear, everyone? Now, everything is super easy. You just find it. So, you divide 30. Oh, it's 40. 40 divided by 0.38 and 0.26. So, it's 0.12. What you get is 330 joules per gram. Any questions now? Please let me know. Okay. Now, kids, the last one is, it says the rate H of thermal energy gained by ice. Now, that's very simple. You can use any equation now. The first equation that we created was 70 plus H equals to latent heat times 0.26. We have the latent heat of fusion, so 70 plus H equals to 330 times 0.26. Now find H easily. So 330 times 0.26 minus 70 will give us 15.8, which is 16 watts that was lost. You get it? Okay. So, Salmasti, whenever you have two values, remember they're going to ask you about this. You have to include this. Get it? Any questions now? All right, let's try to absorb this. Okay. Okay. Everybody understands this completely. Abu Bakr, everything is clear. Aisha, Samir, Zainab, Salma. Should I go forward, please? Okay, very nice. Samir, wake up, please. All right. So, going to the next now, we're going to talk about the first law of thermodynamics. First law of thermodynamics, this is the last thing we're going to do today, okay? And then we'll continue from the rest tomorrow. The first law of thermodynamics states that the increase, in fact, the increase in internal energy of a system equals to the sum of heat supplied to the system and the work done on the system. Okay, so I'm gonna color few things here. So first thing is state the increase. This is I'm just gonna color the keywords right here. Okay, so color blue. Okay, so increase in internal energy. So this is also keyword of a system equals to the sum of heat supplied to. If you see this, obviously that is also a keyword. So underline a color, the system and work done on the system. So if it's written work on the system, that would be also a keyword, just like this. Okay, so this is important. That's why I've just highlighted it. What it truly means is that the change in internal energy, if it's increasing, so there's a positive sign, would be equal to change in Q plus work done. So let's talk about it. So this gets is the increase in internal energy and this would be the heat supplied to the system and that would be the work done on the system. So these are the symbols that you guys need to remember. All right. Let me know if you have a question. Okay. Now I want you guys to fill this table up. So I don't know where the line went. So just put a line here. You will have Q positive if it is written in the question that heat is supplied to the system. If it's written heat is lost by the system or supplied by the system, something like that, that it would be negative value. Delta U will be positive if internal energy increases, and it will be negative if internal energy decreases for work done. If it is written work is done on the system, and if it's written work is done by the system. So it will be negative then. All right, kids. So last thing, work is done on the system when system is compressed. Compressed means decreases in volume. And work is done by the system when system expands, which basically means increases in volume. Yeah. So this is what you got to write. All right. So this is basically everything that we got to do today. So if you have any questions now, please let me know. All right, kids. So I think I will see you now in